So welcome to this new question, critical connection. Critical connection. In this question, what we have to do? We have to do just one thing. Here, the one has how many connections? So what is the critical connection? When we remove this, when we remove any edge, then the graph should be divided into two parts. So this edge is called a this graph is called a critical connection. So this edge is called a critical connected edge. Okay. So when we remove any edge, then the graph is divided into two parts. Then that connection is called a critical connection. This edge is called a critical edge. Okay. Like this part, if we remove this edge, then this graph is divided into two parts. The graph is divided into two parts. So this is our critical edge. This is our critical connection edge. Okay. So you understand what is a critical connection? So what is the difference between articulation point and critical connection? In articulation point, we are removing any edge, we are removing any vertex like this. If you remove this vertex, then this graph is divided into two parts, and this is called a articulation point. Okay, so this is the difference between critical connection and articulation point. So how we can solve this question? So this question, what we have to do? What we have to do is, in this question, same, we have to find three things: low value, and we have to find three things. First is low value, and the second is discover value, and the third is parent array. Okay, so three things: low vertex, low value, discover values, array. So we have to find three things: low array, low value array, discover value array, parent array. Okay, so how we can find this thing? Initially, what we are doing, we just update our low value. We update our low value equal to discover value. Okay, so what is our discover value? Discover value is a stage where our value is discovered, where the vertex is discovered. Initially, this vertex is discovered at 1 stage. This vertex is discovered at 7 stage. This vertex discovered as 3rd stage. This vertex discovered as 4th stage. This vertex discovered as 5th stage. This vertex discovered as 6th stage. This vertex is discovered as 7th stage. This vertex is discovered at 8th stage. Okay. Initially, we made a low value equal to discover value. What is the minimum? What is the value of? What is the meaning of low value? Low value means when any vertex calling the point to a minimum vertex. When any vertex point to a minimum vertex is called a low value. Like 2 will point itself, but what we have to do? We have to just ignore the previous path. Okay, so we have to just ignore the previous path, and we have to find the low value. So how we can find low value array? We have just go and make initially we make a discover value equal to low value. So low value equal to 1. And here also 2, here also 3, here also 4, here also 5, here also 6, here also 7, here also 8. But at some stages we have to update the low value. At which stage? We have to just put our conditions, like if. So for ignoring the path, like when we call 4, then how we can decide our low value? First, we have to ignore the path of previous path. We have to just ignore this path, and then we have to update our array. First, I have to tell that you have to just go and watch the articulation point video. Then you have to just come here. Okay. So if 4 has, like if our neighbor, like what if our parent array, if our parent, what I'm saying, if src, if our neighbor, what I'm saying, if our neighbor is parent, then we have to continue. Our neighbor is parent, then we have to continue. Else, if our neighbor is wasted, then we have to update our low value. Okay, then we have to update our low value with its low value, our low value, and discover of neighbors. Okay, discovery value of neighbors. And the third condition is else if. Else if in the third condition. What is the third condition? Third condition is else if here, and else in this condition we just call a DFS. We just call a DFS, and where we just get at another neighbor, and when we are backtrack it, then we have also update our low value with minimum of own no value. It means low value of RC and low value of neighbor. Okay, and then we just check out what is our critical point. Okay, so the whole thing is like after, so the whole thing is same as critical, same as articulation point. Okay, so which cases will remove, like when we call at this stage like 2 times, because we are not finding any node, we are finding an edge, so we are just calling, we are just removing the edge conditions. Okay, so in the critical connection, so when we are going to find a critical connection, we have to care about some things. Like when you in the articulation point, what is the condition to find out critical? What is the condition to find out articulation point? If the low value of neighbor, is greater than or equal to discovered value of SRC, then this is called a critical, called a articulation point. Articulation point. Okay, this is called articulation point. But here what? Here we are not provide this check. Only that this is the only difference, that here we not provide this check. Why we are not providing this check? Then we can find out critical connection. Why we are not providing this check? In first we understand how we can find articulation point. Okay, so at the stage of this, what we are waiting, our neighbor, like we take a 2, and the low value of 8 is like 7. I think the low value of 8 is 5, 6. The low value of 8 is 6 and the low value of 2 is 5. So why 2 is our articulation point? When we remove 2, then the graph is divided into 2 parts. So this is articulation point. But why? We check at this condition. The 2 have two neighbor 6, but this is our parent. So we have to ignore this path. Okay, and when we ignore this path, then we have to check out our another neighbor, which is 8. If the discovery value, if the low value of this neighbor is greater than or equal to discovery value, like 2, like the discovery value of 2 is 5 and the low value of 8 is 6, it means it cannot go here. Because the discovery value is, the low value is 6. It means it can be minimum point to 6. It cannot minimum point to 6. It cannot point the minimum value of 6. Like it can point only 6 to 7 to 8. It cannot point 5, 4, 3, 2, 1. Okay, it can point 5 because we put a condition of equal. This is the region we remove this equal. Why? It can point to 5. It can point 5. But if it can point beyond the 5, less than 5, then it is not a critical point. Then 2 is not a critical point. But if the low value of neighbor is greater than or equal to discovery of source value, then it can be articulation point. Because if the reach of 8 is beyond than 2, then it cannot be articulation point. So reach is limited here. If reach is at this stage, then it can be articulation point. But at the term of h, this condition is not valid. We have to remove this equal condition. Why? Because when we put a equal condition now, then it can check here. But when we remove this, then it can go from another edge. Now it can go from 5. It can go from 5 to 2. It means the low value of 8 could be 5. From that node. What I'm saying, you just understand. Suppose this 8 has low value 5. Suppose this 8 has low value 5. Then how low value 5? 8 is pointing to 5 and 5 is pointing to here. So if 8 has low value to 5, then it can point to 2. Then the low value of 5, 8, then the low value of 5 is greater than or equal to NPR. Then also 2 is articulation point. But at the term of edge, this is not a critical connection edge. Because when you find out, if you put equal condition, then it decided that this is our edge. But when we remove this edge, then this graph is not divided into two parts, because the reach is the equal condition will make the graph from that part, will tell us that edge is connected with this edge. Okay, so when we remove this edge, when we remove this edge, then also the graph will connected. Okay, so we have to not put a equal condition, because equal condition can make we using another edge. Okay, this equal condition tell us that 8 can be go to this graph equal by this edge. Okay, so we have to just remove this equal condition. We have to just remove this equal condition, and all thing is same in the articulation. So we have to just go and code it. Okay, so I think you have to just understand everything. So now we are going to code this problem. Okay, thank you so much. So I'm going to code it. So now we are going to code it. So we take a discovery value of u. It means it is initially equal to low u. It means we just update our discovery. We just update our low value equal to discovery value in the initial side. This is the same thing we are done with the find out our optimal. We have find out our optimal like articulation point in the graph. Okay, so in this point we take a vested u equal to true. Okay, why we are taking a vested u equal to true? Because we are just come at this stage initially. Okay, after that we are find out our all odd edges. Okay, we are just taking our find I equal to 0, and then we are just find out our all edges. How we can find out our all edges? Using this size of graph, and then I take I plus plus, and then what we have to take? We have to just find out our first edge. How we can find out our first edge? Into v equal to graph. Into v equal to graph. Graph dot u dot graph dot u dot I. Okay, so at this stage, graph dot u at this stage we have found out our first edge. Okay, after that we have to just check out that if our neighbor is our parent. If our neighbor is our parent, then what you have to do? We have to just continue at this stage. We have to just continue at this stage. What I am saying that if our neighbor is our parent, then we have to just continue at this stage. Okay, we have to just continue at this stage, and also we have to just check out another condition. What is condition? If our vested, if our edge is vested, if our edge is vested, then what we have to do? We have to just go and update our low u. Update our low u with minimum value of what? With minimum value of our low u. With minimum value of our low u, and discovered value of v. Okay, so this is the condition when our edge is vested. Okay, and after that what we are doing it, we have this else condition. We have put another else condition. Why? This else condition is for checking that our call the DFS calls. Okay, so this is the condition where we call the DFS call. Okay, then we have to just call parent of u equal to v. So at this stage what we are doing, we just call parent v equal to u. It means here are we create an array of parent array. Okay, we are creating a parent array. Okay, so after that we are checking what we are getting, and this is our depth plot. Then we have to call again and again. Then we have to call the braces again, because this is our depth call. This is our where we call a depth DFS. Okay, so there are we call it DFS like u comma. So that is the stage where we call a DFS like v comma graph comma answer. Okay, and after that what we are doing, we just check out our condition of critical point or a critical point. Okay, if low of u is greater than discovered value of u. Okay, so low value of v is greater than discovered value of u. Okay, at this stage what we are doing, we just take our vector of int data type, and then we just take a temp. Then after that we just take a temp dot push back u, then temp dot push back v. Then what we have to do, we have to just again go and then temp dot push back, what back, temp. So this is the value which should be pushed. Okay, so this is your condition where we just call it again and again. So what we are taking is, we are just initially we take a disk u equal to low u equal to timer, and then we increase the timer plus plus, and then we take a visited u equal to true, and then we put a graph where we put a graph u dot size, and then we just initialize, we just take a vertex and we check our parent u equal to b condition, then we continue from that part, and then we check else agar if visited v equal to true, then we just update our low u according to min u, and then we just check parent v equal to u, then we just check out bridges v comma graph of answer. Okay, we just call it again. So we got in some error, so we just put a comma, so we just go and run it, so accept it and submit it. So this is submitted. So now you understand what I'm saying to you. So first we have to just go and now I'm just telling out that how this code is run. So first we have to just go and like this. Sorry. So we have to just go and crop this code, and then I'm explaining the whole thing. Okay, so this is your code. So now I'm explaining the thing. So how the code is run. Okay, so initially what we are doing, initially we just take a discover value. Initially we just take a discover value and put a low value, same thing, like initially this is 1, this is 1, this is 2, this is 3, this is 4, this is 5. So initially we update our discover value equal to low value, and then after that we just increase the timer. This timer will increase according to our DFS call, and every time our timer is updated, and then this timer will provide value of 1, 2, 3, 4, 5, 6, 7. Okay, and after that we put a visited u equal to true, which tell us that our node is visited, everything in the articulation point, and then we find out all edges. Then we are finding out all edges. From that part we find out at this stage we find out 1 to 2, 2 to, and at the stage of 2 we find out all edges like 2 to 4, 2 to 1. Okay, but we are checking out that our edge is our parent or not. If our edge is our parent, then we just continue, and then also we check out that our edge is visited or not. At the stage of 6, this edge is visited, 6 1 is visited, so we just check out this edge and then update our low value. And after that what we are doing, we just update our parent array, and then we call a DFS again for our neighbor. Okay, after that we are update our low value. In the articulation point also we are update our low value, same here. And after that we are just put a condition to find out our critical connection. Just the difference between articulation point and critical connection is we remove this equal sign, and all of them is same. Okay, thank you for watching this video.